Good morning, everyone. My name is Elena Franchin, and today I'm going to talk about my research project on the impact of the size constancy mechanism in perception and action. My area of research is neuroscience, with a special focus on visual perception and specifically on how we perceive objects and how we use this information to interact with the world around us. The objects on our retina appear of different sizes based on the distance from which we observe them. Because if you think, for example, about when you throw a boomerang, even though it appears smaller when it moves away and larger as soon as it comes back, we know that its size isn't actually changing. And also, when we reach out to catch it, our hand seems somehow to know how much it has to open to properly grasp it. This mechanism is known as size constancy, and it happens because our brain uses visual cue to judge the distance of object. But what happens when those cues are not available? So, to explore how the brain combines different types of information to build perception and guide action, we designed an experiment in which we recorded participants' brain activity and movements while they were asked to grasp some sphere or indicate their perceived size, always using the right hand. In addition, we asked them to hold the pedestal on which the sphere were placed using their left hand. The tricky part of the experiment was that even if the sphere were of different sizes, the two retinal images that they projected onto the retina were identical. Also, we tested participants under both natural viewing condition and in the dark, making them wear a pair of glasses with just one tiny hole in the right lens so that they could see only through that. And it was almost like looking through a keyhole. Also, we used the screen that became opaque as soon as participants started the movement. So participants could see neither their hand nor the sphere while performing the task. And here you can see a couple of examples of the two experimental tasks.
Baseline, up, baseline, up, baseline, up, baseline, up.
Okay. First of all, we found that in just 150 to 200 milliseconds, the brain could tell the difference between two objects of different sizes, even if the retinal image was identical. Additionally, we observed that in the restricted viewing condition, the brain activity seemed somehow to match the retinal size of the stimuli, while the hand adjusted to the object real size. And also, we found that participants were faster in reaching the bigger sphere, which was also the one placed the furthest away. So, the importance of this research in terms of scientific impact is in gathering further evidence that can be implemented in the development of theories on how the brain generates object experiences, paving also the way for innovations like human-machine interfaces and teleassistance systems that are crucial not only for fields like telesurgery, but also for the development of prosthetic devices. From a clinical point of view, this advancement can drive new multisensory rehabilitation techniques for neurological patients, and also the development of virtual reality technologies for training in high-risk fields. Furthermore, this innovation could be applied to enhance driver safety and improve navigation systems, contributing to safer and smarter environments. In conclusion, the convergence of neuroscience and technology holds enormous potential to transform both scientific discovery and healthcare, benefiting society in profound ways. Thank you very much for your attention, and a special thanks to my colleagues who helped me throughout this whole huge project.